So, in the last few classes we were talking about logical reasoning and we understood inductive logic, deductive logic and a part of deductive logic, syllogistic logic, we understood those things. But today we will deal with the question, in science we are trying to find out truth, but our method is by applying logic, applying valid logic. The question is truth the same thing as validity? No. Something being true does not imply the logic is valid, and when the logic is valid, that does not imply the statement is true, and we will illustrate that with some examples. So, the main point that I am making is the truth is not the same thing as validity, not the same thing as validity. Let us see. Let us start with a logical reasoning. Let us say all dinosaurs are mammals. Obviously, a incorrect statement, false statement. Then we say all cats are dinosaurs. Then by valid logic we can conclude, by eliminating the middle term, joining these two terms, we can conclude that all cats are mammals. See, this is a correct statement. Valid logic, correct statement, but you see the starting premises are both wrong. This leads us to the conclusion that incorrect premises can lead us to correct conclusions, but if the method is valid, the logic is valid, then from correct or true premises you cannot arrive at invalid or incorrect, untrue, false conclusions. And that is the power of logical reasoning. Starting from true premises, you always arrive at true conclusions, but this is also true that starting from incorrect premises, you can arrive at a valid and correct conclusions. But is the converse true? In order to see that, let us do a process, do a reasoning. All particles with integer valued spin are bosons. And the minor premise is electrons do not have integer valued spin. Therefore, electrons are not bosons. Is this logic valid? That is the question. All particles with integer valued spin are bosons, that is a true statement, scientifically correct. Electrons do not have integer valued spin, its spin is 1/2, therefore, it is not integer valued. This is also a scientifically true statement. Is this statement correct? Yes, it is also a scientifically true statement, but is it logically valid? In order to test that, let me do something. Let me give one more example where the logical structure is exactly the same. I will say all insects are living organisms. And then we will say as a minor term, tigers are not insects, are not insects. And then based on that we conclude, therefore, tigers are not living organisms. Living organisms. Is that conclusion correct? Well, obviously, tigers are not living organisms is a incorrect, untrue conclusion, but you see all insects are living organisms is correct. Tigers are not insects, that is also correct, and yet we have come to a conclusion that that is wrong. Obviously, this is a invalid logic. So, this logical structure is invalid. How do you conclude that it is invalid? Let us just check quickly. We draw 3 blobs and try to work it out the way we have learned how to do that. First one, let us do this one, all particles with integer value spin. So, let us call it I, integer value spin, are bosons and electrons. So, these are the 3 blobs. The first statement is all particles with integer value spin are bosons, all. Therefore, all those things that have integer value, but outside bosons will be blocked off. There is no element in this part. Electrons do not have integer value spin, which means the overlap between electron and integer value spin should be also blocked off. Now, let us examine whether this statement is correct or not. Electrons are not bosons. In order to say that electrons are not bosons, this part also must be blocked off, but it is not. From the premises, we do not have the ability to block it off or to say that there is no element here, and therefore, this statement is definitely wrong. It is invalid logic. So, you notice that here all the statements are correct, both the premises as well as the conclusions are factually correct. That often leads us to erroneously conclude that the logic is also valid. It is not, and we have to practice therefore to separate validity from truth. The judgment on validity should not be influenced by our understanding of what is true and what is false. This leads us to conclude that correct, true statements by valid logic will only lead to true conclusions. False statements using valid logic, we can obtain true statements. So, we conclude that therefore, let us logically argue from the opposite end, the conclusion being false implies that the premises are and the conclusion being true does not imply that the premises are true. This is very important for science because in science we propose hypotheses and postulates, ultimately that cannot be directly tested, and so we logically derive certain results by deductive logic. Starting from that as a premise, we derive certain results which can be tested, and we test that. So, when we test it, this means that the conclusion can be tested to be true or it can be to be false. Now, if it comes to be false, we can conclude that what we started from, the hypothesis or the postulate, is false. But if the results after experimental test turns out to be true, that does not imply that the hypothesis or the postulate is true. We had arrived at the same conclusion when we were talking about modus ponens and modus tollens. We concluded that if A then B, if it is given, then if we see that not B is true, then we can conclude not A. But if A then B, and if B is true, then we cannot conclude A, it is false. So, here using syllogistic logic, we are arriving at the same premise, same conclusion. This is extremely important for science, because in science we really do not have any option but to use logic, and we have to remember that when a logically derived result turns out to be true, that does not imply by this, does not imply where we started from, that is the proposed hypothesis or postulate is true. We have to keep on checking and rechecking. We have understood application of inductive logic and deductive logic. Both applied together leads to logical reasoning. Now, when we apply deductive logic, we always start from some inductively obtained premise. When we apply deductive logic, we have to have some inductively obtained premise in hand. That is why inductive logic is known to be prior, and then we can apply deductive logic. Even though that is the structure of logic followed in science, some philosophers have raised question regarding the use of inductive logic. The reason is that they said that after all, science tries to arrive at truth. So, we have to be certain that the conclusions are correct. There is always some doubt regarding the conclusions arrived through inductive logic because of the inductive leap involved. So, some philosophers said forget about inductive logic, use only deductive logic, and yet science has really progressed using both the logical structures. Let me give some examples. Field biologists have found that every species occupy a single niche. Every species occupies a single niche. Niche means what it feeds on, what kind of environment it thrives in, what kind of predators are there. So, all these put together is the niche that a organism survives in. Now, if now this was obtained through inductive logic, a few cases were obtained where people noticed that each species is occupying a single niche, and so they generalized it and said that it is a general conclusion. And that has allowed people to actually field biologists, when they explore new areas and if they see that two or three different species are living in the same area, eating the same grass, say Thomson's gazelles and wildebeest and say zebra, they always look for where their niches differ, and they have always found one. So, this inductive conclusion actually led people to do proper science. It has given directions to science. But there are areas in which you cannot do without it. Let me cite an example from astronomy. How do we measure distances to stars? Well, distances to nearby objects are found by the method of parallax. For example, we see with our two eyes, suppose these are the eyes, and there is an object here. You notice that these two, this line and that line, make an angle, and that angle is called the parallax angle. And in order to measure the parallax angle, or it being measurable, this distance should not be too large, or if there are larger distance, one has to increase the distance between the two eyes. For example, the distance to nearby stars were measured by actually taking a photograph from in summer and taking another photograph in winter, and by that time the art would have in an elliptical orbit, the art would have moved around the sun. The art, once it is here, another time it is here, and obviously then the distance between the two eyes becomes the diameter of the earth's orbit around the sun, and that way the distance to many stars could be measured. But even that distance becomes too small to measure the distance to even farther stars. So, they could not be measured. So, for some time science was facing a roadblock, it could not go further. At that stage, one scientist, Henrietta Leavitt, she was studying what are known as Cepheid variable stars. What are Cepheid variables? The stars that pulsate, that oscillate. Their intensity of radiation oscillates, goes up and down at a constant frequency. Sometimes it is days, sometimes it is hours, sometimes it is weeks, but it has a constant frequency oscillation. What she did was, she identified some such stars, Cepheid variable stars. So, she was talking about Cepheid variables. The Cepheid variables that she studied were within the range to which it could be measured by this method. So, she knew the distance. If you know the distance and if you can measure the apparent luminosity, then from these you can find out the absolute luminosity, the amount of light it is emanating. Now, then she tried to figure out if there is a relationship between the apparent luminosity and the absolute luminosity. She measured the distance, and from there she actually obtained the distance, from there she obtained the absolute luminosity. So, absolute luminosity. and in the x axis she plotted the period. Then the curves she got were like this. Which means that there would be variable stars located in these parts. So, ultimately she could fit a curve. And you would notice that this kind of curve would become a straight line if you take the logarithm of the period. So, she could fit into a logarithmic curve. So, it will be like if you take the ln of the period, then it would be a few lines, few points, which will ultimately allow you to draw a line through that. So, this is what she obtained, that there is a definite relationship between the period and the absolute luminosity. Now, other astronomers said that now we have a way of measuring even further distances. How? Because even further distances we can see the Cepheid variable stars, and therefore, by simple visual observation or telescopic observation we can find out the period. And if you can find out the period, and then we can find out the absolute luminosity, and if you can find out the absolute luminosity, and if you can by observation measure the apparent luminosity, we can find the distance. Now, notice the logic they were applying. What Leavitt did was to obtain a relationship applicable for a few Cepheid variable stars. Other astronomers said that let us assume that this is a general relationship valid for all Cepheid variables. Thus, there was an inductive leap, there was an inductive logic involved. The moment they had that inductive logic applied, then for any particular Cepheid variable, they would simply apply that relationship and obtain the distance to that Cepheid variable. And if that variable star is a member of a globular cluster, that allows you to measure the distance to that globular cluster. If it is a member of a galaxy, you can measure the distance to the galaxy. In fact, that is what Edwin Hubble did. When he started observation on the Mount Wilson Observatory, he turned his attention to the nebula called Andromeda Nebula. At that time, it was known to be a nebula, a fluffy, fuzzy object. And when he did that, he saw that it is a cluster of stars, and he could isolate individual stars. He could see individual stars, and he could identify a few Cepheid variable stars. The moment he could do that, he could apply the same logic and he could measure this distance. Thus, he could measure the distance to the whole Andromeda galaxy. In fact, today all galactic distances are measured this way. In fact, the Hubble's law, on which the whole of cosmology is based, is also measured this way. Now, notice that this is a typical example of application of inductive as well as deductive logic. We obtain the general law by generalizing the observation on a few Cepheid variable stars, and then when a particular Cepheid variable is obtained, then its distance is measured by applying deductive logic. Science actually works this way, and you would notice that without using inductive logic, in this case there is no way to measure the distance to further objects. So, science actually thrives on joint application of inductive as well as deductive logic. But in applying inductive logic, a scientist keeps his or her mind open to doubts, since there is an inductive leap involved. Therefore, there is always an element of doubt. In fact, in this case also it happened. Later it was found that Cepheid variables are not just one class of stars, there are actually two types of Cepheid variables who give different curves like this. different relationship between absolute luminosity and the period of oscillation of its intensity. And so, therefore, depending on which type of Cepheid variabilities, we had to apply a different relationship. For that, we had to keep the mind's eye open, harbor an element of doubt. The moment you have doubt, you test, check, recheck, and finally, if there is an error, you correct it. This is how modern science functions. By applying both inductive as well as deductive logic, but whenever there is an application of inductive logic, there is an element of doubt, therefore, there is a question of checking and rechecking. But whenever we have a premise given by inductive logic and we apply deductive logic on it, then its logical structure is that if the inductive premise is correct, then the logical deduction must be correct. And we progress in science by applying both inductive and deductive logic. Thank you.